So we want to extend the quantum decomposition induced by a probability measure on R on a single random variable to the case of D random variable. The case of D random variables, there is a part of this extension which is trivial. Just you or generalize the Gram-Schmidt procedure, and there is a huge literature. Well, not so huge as in the one-dimensional case, but now, especially in the last 10 years, many books on multidimensional polynomials, orthogonal polynomials, have appeared. However, as I will try to point out, the standard approach has many insufficiencies. The approach that is proposed here is, has been developed in order to overcome these insufficiencies, and you will see that it brings some interesting and unexpected results. So I fix notations. In the following, D will be the finite set of the first D natural numbers, and P will be the algebra of polynomials in D indeterminates. We identify this algebra with the polynomial functions on some concrete RD, as we have already said in my first lecture. I will save several results, since the discussion will be rather long. Several results I will recall of this discussion from my previous lecture, because several results I developed in a language that is applicable to multidimensional case. So we will save time. Okay, so we put X to this algebra by definition has an algebra with identity which corresponds to the 0 power of all the polynomial functions. After that, we introduce a fundamental notion of monomial, algebraic notion of monomial. So we have a set D, which is finite. So we have a finite product of the D variable. You can think of xj as a random variable. For the moment, they are not random variable because there is no measure. The discussion will begin at a purely algebraic level. Okay, so this is a monomial, xj power nj, and the product over all possible j. When the sum of j of all j is equal to m, we speak of a monomial of degree n. And then we introduce the set of all monomials of degree less or equal n, and then the set of all monomials of degree exactly equal n. The vector subspace generated by the monomial of degree less or equal n will be denoted by P with this bracket to denote that all the lower order, all the order, the polynomials of degree less or equal than n are obtained. Then we use P0n to denote the linear span of the monomials. So you take all the monomials of degree exactly n, and you take linear combinations. The monomials are linearly independent for a fundamental theorem of algebra, which is so-called the theorem of identity of polynomials. If two polynomials are equal, equal if and only if they have the same coefficients. So this is equivalent to say that the monomials are linearly independent. And this theorem holds also in the multidimensional case. the linear span of monomials will play an important role in the following. For example, the monomial of degree 0 is only the identity. So the monomial, the vector space generated by monomial of degree 0 coincides with the vector space generated by the monomial of degree less or equal than 0 and coincides with the multiple of the identity. In general, it is a well-known fact that if you have the cardinality of the set D is equal to M, in our case is equal to precisely D, but this is true for every D, then you have exactly this is the dimension of the space of the linear space generated by the monomial of degree n. For future use, I emphasize the fact that this number, dn, is exactly the dimension of the symmetric tensor product of m copies, of n copies of a space, a complex of C to the power m, the complex number to the power, the vector m-dimensional complex vector space. This will be used in the following. Now, I introduce another notation. I hope that will not create confusion. When there is this possibility, I will change and use a more complex notation. So the set of polynomials is an algebra. Every algebra acts on itself by left multiplication. Okay? And I will use the same symbol for the algebra, the element of the algebra, and the operator induced by left action. For example, the coordinates, I will denote xj, either if I consider as an element or if I consider as an operator. Sometimes, when I want to emphasize that I consider the element of P as elements of vector space, I will use this notation. I write, instead of Q, I write Q dot identity, or Q dot phi 0. Phi 0 is the identity, is the only element of the vector space of the monomials of degree 0. So, as we have seen last time, the degree filtration, the degree defines a filtration, because of course any polynomial of degree n minus 1 is also a polynomial of degree less or equal n. So any polynomial of degree less or equal than n minus 1 is also a polynomial of degree less or equal n, and therefore we have increasing filtration. On the other hand, every polynomial is a finite degree, therefore this union takes place in the set theoretical sense. This filtration is compatible with the degree in the sense that if I multiply two elements of the filtration, I get the element corresponding to the sum. It is extremely important to know and to notice that if I have my P, which is PD, I have used P as a synonym, as the same as PD, our polynomial algebra is the direct sum of the, we have a so-called monomial decomposition or monomial gradation. That is, the direct sum, I use a sum with a dot to distinguish from orthogonal sum. Okay? This is in the sense of vector space. So what is very important to notice is that the monomial gradation, well, it is a simple calculation. I will not do it here because we have no time, but you can do it as an exercise. There exists a single measure for which the monomial gradation is orthogonal. And this is precisely the delta measure at 0. Okay? So the monomial gradation can be orthogonal only for trivial measures. What we will see is a very interesting point, is that if I make a small perturbation of the monomial gradation, that is, I subtract to every monomial a polynomial of degree strictly less of the monomial, I get a new gradation, and this gradation are in one-to-one correspondence with orthogonal gradations. Okay? So now we will come to this point. So okay, this is gradation in the direct sum sense. So obviously, only the zero polynomial can be linear combination of monomials of different degrees. And of course, any polynomial of degree less or equal than n is a sum of monomials, of a linear combination of monomials, or in fact multiples of monomials of degree less or equal than m. So you have an important point that will be shared by the orthogonal gradations, that the monomial gradation is compatible with the filtration. Here should be written n plus 1. N plus 1 has been dropped down. Okay, so the correct statement is the p of the monomials of the polynomials of degree less or equal than n plus 1 is the direct sum of the polynomials of degree less or equal than n plus monomials of degree n plus 1, exactly. Well, no, this is correct because I am taking the sum over all k greater than n. But in fact, a more precise result is true. Maybe I wrote it. In fact, we will use it very much. No. The more precise result is that for every n, we have that p n plus 1 polynomial degree less or equal than n plus 1 is p n direct sum p 0 means monomial n plus 1. So this is true for every n. And it will play an important role in the reconstruction theorem. So to give the coordinate functions is equivalent to give a linear map from the d-dimensional complex space into the linear. Here I want to consider them as a linear operators on P. Because when we think in the terms of quantum mechanics, P will become the Hilbert space, in general the Fock space, and linear operators over P. These linear operators are called usually the field operators. Okay? So this is just to make a connection. But we will use, therefore, interchangeably the notation, either a linear map from CD into the linear operators on P, or a given we have D different self-adjoint operators. This linear map is is very important to emphasize that this linear map is compatible with the real structure on the polynomial algebra P. That is, it maps polynomial with real valued coefficients into polynomial with real valued coefficient. Now let us do an important connection, which will, in some sense, anticipate. It is a well-known algebraic fact, but it lies at the basis of the theoretical basis of the emergence of the usual boson-Fock space. So, as I said, there is, of course, a natural real structure over a complex number. Real structure means that the complex number is a direct sum of two one-dimensional real subspaces. And this gives an involution. So this real structure induces a real structure on the d-dimensional complex vector space with the component-wise involution, obviously defined. So in the following, we fix this dimension, d, and we only consider, and we also fix the basis, which is the canonical base. Canonical base is a particular case of a real basis. Real basis, when we speak of a real basis of CD, we mean that we have a set of vectors in Rd, which is a basis of Rd. Then automatically the complex linear combinations will span CD. Not all bases are real bases. Okay? We will use, important that in the orthogonal polynomial, the bases that appear are all real. Remember, how do you obtain an orthogonal polynomial? You subtract from a monomial of degree n all the components on lower degree. But what is how is obtained the component? By taking the scalar product. The scalar product for a probability measure of two monomials is a real number, because it's a moment, it's a mixed moment. So it is a real number. And so the orthogonal polynomials are all polynomials with the real coefficient. This will be important. So we define the tensor for each n. So we define the tensor algebra as the direct sum in the linear space sense of the vector space, which are the nth tensor power of CD. On this direct sum, we define a multiplication as a tensor multiplication. And this gives us an algebra structure. The algebra structure is in some sense canonical. The star algebra structure is not canonical. There are many involutions that I can put on the tensor product algebra. We will choose this one, which keeps the order. But for example, if I flip the order, I will obtain another involution, which is also possible definition. There are many possibilities, okay? So we will take this one, in which the order is not flipped, and the real elements are those who are invariant under the involution, corresponding to tensor product of real vectors. So we have a star algebra structure. And this star algebra structure is called the symmetric tensor product of n copies of CD, or simply the tensor star algebra. You can prove, this is a simple remark, by the polarization identity. Of course, the linear span of the algebra generated by these vectors is contained into the symmetric tensor algebra. The converse is true. This follows from the so-called polarization identity that allows to express any symmetric n-linear map as a linear combination of restriction of the same symmetric map on the diagonal, where all elements are, or any elements are equal. Okay, this is called polarization identity. And another characterization, as I said, is that if this will be, we will consider in the following. This is the standard characterization used in the definition of boson-Fock space. For each n, you define an action of the permutation group. You take a permutation sigma, and you define an action on the tensor product of n copies of CD simply by permuting the indices. And the symmetric tensor product is defined by the condition that this that is the subspace of the standard tensor product that we have just defined, which is fixed under this action. So from the tensor algebra, taking the fixed point of this action, we get the symmetric tensor algebra. So the symmetric tensor algebra is a star algebra. And now the bridge between symmetric tensor algebra and polynomials is given by the following lemma. The lemma says the following. Remember, EJ is the canonical basis of CD. If I associate EJ as an element of the symmetric tensor algebra, because of the symmetric tensor algebra is an abelian algebra. Since I take the symmetrization of the scalar product, the order doesn't matter. You can intuitively see. The formal proof will follow this intuition, okay? So the symmetric tensor algebra is an abelian algebra. You can say you can identify it with the so-called free abelian algebra with generated by D elements. So the D elements we identify to the basis of CD, and we take the free abelian algebra with identity, and we identify with the polynomial algebra. So how do we identify? Simply identifying the generators. So this gives, by the way, here comes in the important point that this is not an arbitrary basis, but a real basis, because it's invariant under involution. So I can extend the algebra isomorphism induced by this identification of generators by the requirement that this identification, that EJ is a self-adjoint. We know EJ is self-adjoint because the algebra is a real. Not the algebra, sorry. The canonical basis of the CD that we have fixed is made by real, 0 and 1. Okay. If you look at this isomorphism, of course, since you map generators into generators, you map products of generators into products of generators. And so symmetric tensor products will go into product of into monomials. That is products of generators. Remember, this is an arbitrary map. So, as we said, as we have seen in the central limit theorem, many indexes will be repeated, and you will see the power. And since everything is commutative, the powers will arise. Okay? In this sense, monomials, we speak of monomial. Any monomial can be written of degree n, can be written in this way. In many ways, you can calculate how many ways by combinatorics. And now we have this lemma. I will not prove because we already gave intuitive proof last time in my first lecture. The lemma is that there is a one-to-one correspondence between scalar products induced by states on the polynomial algebra and scalar products for which the coordinates are symmetric operators. This we already saw last time, so I will not, because the time is running as usual very much. So now we want to state what it will be our problem. So to this we introduce a generalization of the monomial decomposition. This is the idea of monic subspace. So remember, the monomial space of degree n is the space of linear combination of the monomial of degree n. And the monomial are a real base of this space, because this space is a real structure compatible with the real structure of the polynomials. Now we generalize this notion, and we say that a subspace of the polynomials of degree less or equal than n is monic of degree n if Pn is the sum of this object, but there are two other conditions. First of all, that the Pn is a real basis denoted Bn, such that for each element of the basis, the highest order term is a multiple of a monomial of degree n. So just to understand in what sense we speak of perturbation of monomial basis, I want to write this. So monomial base, a typical monomial base, you take a monomial of degree n. In the quantum mechanical language, these are the non-normalized basis, so-called the number basis. Okay, the orthogonal polynomial will be the number basis. Now you take a monomial. If you take a monomial of degree n, you speak of a monic basis if you have a perturbation, which means that you have an object which is here the monomial is of degree n. So the sum is d. Is n. The sum is n. And here you have a polynomial of degree n minus 1. And here you can allow a multiple, which depends on the monomial itself. Typically, this kind of polynomials appear, as I mentioned before, in the Gram-Schmidt orthogonalization. Because when you subtract to this monomial the components on the lower order polynomials, you have exactly this structure. And C corresponds to the normalization constant. Of course, C can be 0. Because, for example, typical example is when the measure has a finite support. But in multidimensional case, many more exciting possibilities appear. Because the measure can have a support on a submanifold of dimensions strictly less than d. And in this case, the monomials, the space of monomials of the monomials of a degree n will not be all independent, because the support of the measure is in a lower. For example, take a plane, take a k-dimensional subspace, linear subspace. If the measure on RD is supported in a subspace, the typical example is this, or another example, nonlinear example is this. Measure with support in a line is reduced to one dimension. This is one dimension, but is more difficult because the constraint is nonlinear. Locally is one dimension. Okay? So this is the idea of monic basis, and will play a fundamental role in our discussion. And an important point is that, of course, if I take a general basis of the subspace of degree n, I can mix many monomials of degree n. Because you remember, we have the dimension is dn, and dn is a number that grows like n to the power d minus 1, asymptotically with n. Okay? So this can be seen easily. So you can have a combination of many monomials, but a monic base has only one monomial of degree n. This is what happens in the Gram-Schmidt orthogonalization. Okay, so when you have the monomials of degree n, you do the orthogonalization. I don't want to go, by lack of time, into the fact that we do not want to orthogonalize as usual in the Hilbert space level. We want to keep at a pre-Hilbert space level. And the reason of this is that we are looking for a universal model. And you will understand what this is, what we mean by universal model at the end of my talk, of the second part of my talk that will be tomorrow. So the only important point is this, is that I will call, now we are discussing necessary conditions. Tomorrow we will discussing sufficient, that is reconstruction theorem. So what we are discussing today is the following problem. Given a state on the polynomial algebra, what can I say of the orthogonal gradation associated to this state? This is the problem we discussed today. So the first problem is the following. There will be, as we have seen in the examples of the measure with the lower dimensional support, there will be some polynomials or even monomials of zero norm. We don't want to quotient out this, so we keep this in track. And we define the zero norm subspace called n, null space, of the given state phi as the space which have zero norm for the scalar product induced by phi. Then a very simple consequence of the Schwarz inequality is that this subspace is in fact an ideal, because if I have a polynomial and I multiply at zero vector, I think I left the proof, no, I didn't put, but it's obvious from the Schwarz inequality. No, but this is important because not only Schwarz inequality, but also symmetry plays a role. Let me just show why. Because if I have a polynomial that has zero norm for the vector space, for the zero phi norm, okay? Then I multiply this polynomial by x, and I consider the phi norm by some xj. You see, then I consider the modulo. I will, well, then, okay, this will go like xj squared c. Is in fact, the symmetry here is not really essential. Symmetry is not really essential, because you see, by Schwarz inequality, you have that this is less or equal than. So this is the fact that it is an ideal. Symmetry is important because it's a star ideal. It is a star ideal of P. Okay. This also we have proved last time, and I gave the proof in general, which is valid also for the case of arbitrary number of variables. So we have the orthogonal gradation associated to the given state phi. The orthogonal gradation depends on phi. As we have remarked many times, the subspace is monic because it's obtained by Gram-Schmidt orthogonalization. Conversely, is important, if I have a direct sum decomposition of the algebra of all polynomials, and I have so okay, the converse is in this. You can ask yourself, suppose I give you a direct sum decomposition of the algebra of all polynomial, when this direct sum is obtained by a state. Okay? So there is a first answer, preliminary answer, which is simple. We have already seen that the fact that each Pn must be a monic subspace is a necessary condition. Okay? So each Pn must be a monic subspace. Then, on each Pm, there must be defined a scalar product, and the unique scalar product that I define is such that the restriction of the scalar product on each Pn is equal to Pn, and the two different subspaces are orthogonal, is such that the multiplication by xj is symmetric. This again we have seen is a necessary condition. Okay? The two necessary conditions are also sufficient. If I give a single scalar product and a decomposition, the decomposition here is not written, but the decomposition must be compatible with the filtration in the sense that we have written here. Here we have this property we have written for the monomial decomposition, but this property, this condition is necessary. You see, now, this is the monomial decomposition. Now we are giving an arbitrary direct sum in the sense of vector spaces, and we are asking when it comes from the orthogonalization of the polynomials with respect to a given state. The theorem is that it is a necessary and sufficient condition. Now we want to go a little bit deeper. Now we want to associate to each such object a three-diagonal decomposition of the space What does it mean, three-diagonal decomposition? We have already seen that now we look again for necessary conditions. So we are discussing for a given state on P. And we look for necessary condition. Since we have a scalar product, then the scalar product is such that if I have the scalar product on the past filtration, on the filtration of the degree filtration, I define the orthogonal projection on the single variable. This projection must be compatible with the real structure, and they define a partition of the identity in the standard sense. This partition of the identity must satisfy this following property. This is another necessary condition. This we did not prove, but I don't know if I will jump the proof here. But this is an important condition. So this means essentially, what does it mean this? Remember that we have an orthogonal decomposition. So if we have an orthogonal decomposition of P, given, not orthogonal, at this moment we are a direct sum decomposition of P. We are looking for necessary conditions. So we have said we give a single scalar product on each of them. Then we want that this become orthogonal for a scalar product, which is the restriction. If this become orthogonal for a scalar product here, then it means that the global scalar product is uniquely determined by the restriction on each of them. So I give a sequence of this scalar product, but I need a compatibility condition. The compatibility condition is this one, that if the projector on one is 0, all the other one will be 0. Okay. Then we proved the last time the symmetric Jacoby relation. And this is another necessary condition. Because not every decomposition is three-diagonal in this sense. Okay? So we have this, and using this decomposition, we defined in the last time, using this decomposition, summing the three-diagonal decomposition, which is xj times pn. Summing over n, here I get the identity, and here I get the sum of three series of operators. Okay? And these operators are defined to be the creation, respectively, the preservation, and the annihilation operator. Okay? And I formulate as a theorem what I just said. If you sum, you obtain this. And these three operators are defined as these sums. Pay attention that these operators are reconstructed by their restriction on each n part. I will call now either n degree polynomial or n degree orthogonal polynomial or n particle subspace in the quantum mechanical language. So you can guess from this formula how will be the reconstruction theorem. We will try inductively to define this partition. Okay? What will be the idea of the reconstruction theorem? I will repeat many times because it is important, and you will see there are some. The idea will be this. You see, from the quantum decomposition, remember, the quantum decomposition has been obtained by the symmetric Jacoby relation, which is this. And now I will use this notation, the A daga. So I will use x restricted, well, this is xj. I will say xj restricted to n will be a daga j restricted to n plus a0 j restricted to n plus a. Here I should write a minus j restricted to n. Now, you remember the definition of what is a plus, a minus. This is an important theorem, but maybe. Okay, this is the important. Remember the definition of a minus. A minus is just the diagonal element, and remember that we have the convention that if n is equal to 0, p to minus 1 is identically 0. Okay? So a minus is simply a minus j n is p n minus 1 x j p n by definition. So I can write as p n using the symmetry, which is absolutely fundamental of the j, p n minus 1 adjoint. But by definition of a plus, j n to be p n plus 1 x j p n, you see that this is the adjoint of a plus to the minus 1. Adjoint of a plus which goes and minus 1. So what does this quantum decomposition tell us as a fundamental point? It tells us that if I have a quantum decomposition, a necessary condition will be that a daga j n will be, now I bring this on the other side simply, xj n minus aj j n minus a daga j n minus 1 adjoint. So you see what, you begin to understand now what is the feeling of the reconstruction theorem. Because suppose that you have constructed a daga up to n minus 1. And a0 and a minus is the adjoint of a daga, so it's automatically defined. So up to n minus 1 you have everything. What is the new information you need? You need this information. But once you have this information, a daga is uniquely defined by this identity. Okay? That's the crucial, absolutely crucial remark. That the structure, the three-diagonal Jacoby identity, if you want to reconstruct the step-by-step, then, of course, this is at a vector space level. Then we have to discuss the scalar product, the pre-Hilbert space level. But at the vector space level, as a linear operator, this is uniquely defined. Now, what is the point that this gives more information with respect to what is a standard known in physics? In physics, the typical creation operator is given by, remember that we have the isomorphism of Pn with the symmetric tensor product. I don't remember if I already have proved this or not, but with this isomorphism, yes, we have proved this isomorphism, okay? The monic, for the monic decomposition, in which the monomials of degree n go to the symmetric tensor product and this is the unique star algebra isomorphism which extends this this map. Okay? So what does it mean? It means that multiplication by x goes into EJ in the monomial basis. The typical creator when we usually do quantum mechanics or in free probability or in more or less the typical creator is it goes like this, EJ daga of EJn minus 1 EJ1 is by definition EJ tensor EJn minus 1 tensor EJ1. You see? So in the typical creator we are missing this part that is suggested by the theory by the quantum decomposition. Okay? This makes the difference between the different types of quantization. So why I said this? I anticipated, because this will be the crucial remark for the reconstruction theorem. I anticipated that this formula will be used for the inductive reconstruction of given what will be given should be still decided, but it will be used as inductive reconstruction step by step from a tridiagonal decomposition of degree less or equal than n to the tridiagonal decomposition of degree n plus 1, of degree less or equal n plus 1. And we will have the compatibility between the two given by this formula. So, to explain, and this is the last lemma, I want to, well, since I began a little bit later, maybe we can recover some minutes. So remember our notation. AJN means, in our notation, AJN means that this xj means x of the EJ basis, and the bar n means restriction to the space, not P0n, to the space Pn, which is already orthogonalized. So, the crucial property is this, that it is contained in Pn plus 1. What is an important property that we have? we have that P0 n plus 1 is in fact the linear span of this. And this, moreover, you see, so we know that the range of the creator is in the space Pn plus 1. Let us take the linear span of the range, which is for all possible j in D, and the point is that equality holds, not, okay, not inclusion. The reason is the following. Suppose inclusion is obvious by definition. Suppose that you have a vector in the orthogonal subspace of degree n plus 1, which is orthogonal to the range of the creator for all j in D. And now we use the quantum decomposition, not indirectly, in the sense, since Xi is an element in Pn plus 1, it is orthogonal to all the polynomials of degree strictly less than n plus 1, so degree less or equal than n. So it will be orthogonal to this polynomial and to this polynomial, because this is degree n minus 1 and this is degree n. So from the fact that it is orthogonal to this, I can imply that it is orthogonal to this. But by the quantum decomposition, this is the restriction of the multiplication. By the three-diagonal Jacoby decomposition, this is the restriction of this. And so we have that this is the Xi n plus 1 is orthogonal to all polynomials of degree in the nth orthogonal subspace. However, the nth orthogonal subspace, by definition, I mean, this is true for each m less or equal n. This is sufficient to take for n. Okay, remember the definition of Pn was this difference of these two. Again, we use the same argument. If a polynomial is orthogonal to this difference, but I know that it is orthogonal to this because this has degree n, because this has degree n minus 1, and I multiply by xj, so it's degree n. So it will also be orthogonal independently to this. And therefore, it will be orthogonal to the polynomials that I obtain by multiplying xj to an arbitrary polynomial of degree less or equal than n, because this is the range. Of course, I know that Xn plus 1 is orthogonal to all polynomials, in particular to the constants, because it's orthogonal to all polynomials of degree strictly less than n plus 1, including the 0 degree. Therefore, I can add the constant, and it's a very simple lemma that you can prove. This is obvious in some sense. It's a definition that if I take the polynomials of degree n, I multiply by xj, I take all possible linear combination, and I add the constant, I get all polynomials. Okay? And so Xn is a zero norm vector. So only a zero norm vector can be orthogonal. So what is the precise statement is that essentially if an element is in the vector space and is orthogonal to the range of the creator, then it has zero norm vector. But I can always add the zero norm vectors, and if the range doesn't include zero norm vectors, I will add these zero norm vectors, and I will obtain a range which is the full a polynomial of degree n plus 1. Okay.